I just introduced the concept about one-to-one function to you. Now, the so-called one-to-one function should be defined as that if f of s is a one-to-one function in some domain, that if you have s1 is not equal to x2, that will imply f of x1 is not equal to f of x2. But normally we will use this one. In case if f of x1 is equal to f of x2, we must have s1 is equal to f of x2. S1 is equal to x2. So even though the formal definition is just like this one, but we are more likely using this rule to check if the function satisfies the property of one-to-one. Okay? This is the first part, and I also give you an example that if following the original function f of x is equal to x2 without any constraint, so its original domain should be negative infinity to positive infinity. So in this case, the function will just look like this one. So it will not be a one-to-one because you can see for the same value in the range 1, you can see we have two different points, -1 and +1, to be mapped through this function to the same value. So we will not say this is a one-to-one function. However, if we just set some constraint on this one, you can see if I just focus on the right hand part, then you can see it will follow one-to-one because only 1 can be mapped to 1, 2, +2 mapped to a +4. So it will fit the requirement for the one-to-one property. So you can see in the future, if we just learn about the inverse function for some certain functions, like trigonometric functions, you can see if we just follow the original domain, the function will not be one-to-one. But we can slightly retreat the domain to let the function become one-to-one function, just like this one. If we just follow its nature domain, its original domain, it will not be one-to-one. But through some restriction, we just focus on the right-hand part, it will become one-to-one. OK， 我这边要说的是，未来你会发现有很多函数其实它原生来说它不是1对1，不过这要下学期了对，下学期了，因为这学期现在这一周跟下礼拜而已但是我先给大家一个观念，反正到时候我再提醒大家那这个就是一个典型的例子，它的原生函数 s 平方来说呢，它是一个抛物线函数，它不是1对1，它可以用水平线去测试，对不对？可是你适度的限制它的 domain 范围呢，它就变成 one-to-one。所以我们未来在讲三角函数的时候，6个三角函数，你会发现它其实原生都不是1对1函数。可是我们为了要让它有反函数呢，我们就会限制它的一个范围。那个范围第一个不影响到它原来的 range 的范围，同时呢又可以让它有1对1的性质。于是呢我们就可以让它有反函数有1对1，然后就有反函数OK， so that's time we just talk about here. And then one-to-one, the property about one-to-one is a very important foundation for the inverse function. So here, when we just want to know the inverse function, if f of x is a one-to-one function on some domain with the range R, the inverse function we will denote it as f kind of to the power of -1. But actually, this is not about the power. This is talking about the inverse of a function f. Okay? And for the original function, if the original function its domain is D, its range is R, when we talk about the inverse of f, then its domain will become R, and its range will become D. So you can see the role has been changed. The original range will become the domain of the inverse. The range of the original function will become the domain of the inverse function. Okay, so if you just look at it, you can see for the f function here, we can let 2 to be mapped to 4. This is for the original function f. But for its inverse function, we will use 4 to map back to 2. So it is the typical example for inverse function and the original function. Okay. Then I also told you that if you have the inverse function, the unique function for the function will be unique. We just have one inverse function. We will not have two different functions as the inverse of for the specific function. And if you just try to draw the inverse function, you can see these two functions, these curves for these two functions will be symmetric over y is equal to x. Okay? And then, this is the very important one. Then, since the inverse of f is still a function, so can we just try to get its derivative? So the derivative function for the f inverse, the inverse of f, b will be equal to 1 over f. You can see here it's the original function. We just take its derivative and use the f inverse of b as the input. You can see for f prime of x here should fall into the domain of f, because this is about f, not f inverse. So when we just use f prime of something, here should be the point should be falling in the domain of f or inverse functions range. Okay, so next time we just stop here. Then I will give you an example. Okay, I will explain why we can get this one first. So okay, so why will be why we can have this result. I want to explain why we can have this result. So if this is the original function, y is equal to f of x, then we assume it's a one-to-one function. So that means f can have its inverse. Then so for example, if this is a and it will be mapped to b, so that means f of a will be b. Then f inverse of b should be a, right? By following the definition of the inverse. Then if the original function f can be differentiable at s is equal to a, so that we can say f prime a exists. So that also means f is differentiable when s is equal to a, right? So right now we are just thinking about that. How about then with this we are trying to get, how about f prime f inverse prime of b. right? Because for the original function, the domain should be this domain. For f inverse, it should be here. Here is the range for f, but here is the domain for the inverse of f. Okay, so it's just as I told you, we just change the role for domain and range for f and the inverse of f. Okay, so if you want to get this one, then you can see if we already know f of a is equal to b. So that means f prime, and we also have, so when we have f prime a, means f prime s when s is equal to a. So that will be equal to dy over dx s equal to a. So this part is no problem for you, right? Because we just follow the original definition for differentiation at s is equal to a. Then if you just regard this as a differential, as I told you, differential, we can regard differential as a variable. So we can just move this item from right hand side to left hand side so that we can have dy is equal to f prime a times dx, so that we can have dx over dy when y is equal to b. So y is equal to b means, you can see, dx over dy means, for the original function, your view is from this angle, from x angle. But when you just see about dx over dy, that means your view will be this angle from y-axis perspective. Okay? So when we just want to talk about dx over dy, means I will consider its differential, its derivative from when y is equal to b, right? So when we want to get this one, it will be 1 over f prime a, right? Because you already move this item here, and then we also can move this item from here to here, and then from here to here, right? Then we can get this one. That will be 1 over f prime a. So it will be 1 df over dx when s is equal to a. And s equal to a is also equivalent to f prime, f inverse of b, right? Why? S is equal to a is also equal to f inverse of b here. See? So finally we can get f prime of f inverse b. We can roughly to prove it, but actually from the perspective of curve, you can also see that when we talk about the differentiation at s equal to a for the original f function, then we are talking about f prime s when s is equal to a, means with a very small change in x direction, it will cause how much change in y, that it will be dy, right? So when we just talk about, when we just want to get the differentiation or the derivative from the inverse of f, that will be changed into when we see a small change in y, that will cause how much change in f of x. That means dx. Okay, so it will be very intuitive way to think about the result is that will be the inverse of f prime a. 哦，这个是一个比较稍微正式一点的推导。为什么这个答案是这个哈？为什么为什么这个是对的哈？为什么这是对？稍微比较严谨，其实没有说非常严谨，但是从这个角度来看呢，其实这样推是可以稍微严谨的说明为什么它刚好这个反函数的导数会是正函数取了导数之后放入反函数值，然后呢再取上下颠倒的导数。但是呢，其实如果大家一下子没办法接受这个想法，不妨想一件事情哈，记不记得我们说，你把这 y 等于 f(x) 去看这个曲线的时候，我们说 f prime a 的意思是什么？是 y 等于 f(x) 在 s 等于 a 的时候的导数就是 f prime a， 也就是它的斜率，对不对？那如果我们讲的比较操作型的定义是什么？它就去观察在 s 等于 a 的附近一点点的改变 ，x 在 x 在 a 附近一点点的些许的改变呢，我们去看看 y 方向到底有引发了多少的改变，对不对？这个是我们当初在对导数的时候的定义是这样讲的，对不对？就是我去看 s 方向有一丁点的改变，然后我去看 y 方向的值有多少的改变。最常见的我们之前讲的例子就是，从位移的函数变成什么速度函数，或者从速度函数呢变成加速度函数，都是这个观点，对不对？只不过那时候横轴是 t， 时间是 t， 纵轴可能是位移或者速度，对不对？但是呢，现在反过来反函数，反函数我也想去看一看它的导数是多少的时候，我们不妨想一想，它刚好恰好会是 f prime a 的导数，为什么？你刚刚的观点是一点点的 x 角度在 a 附近的改变那样去观察 y 方向的改变，对不对？当你的角色变了，你从 y 的角度去看 s 的角度的变化量的有多少的时候呢？是不是等同于从 b 看回来，从 b 在 y 的等于 b 的这一点去看回来 s 方向的一些改变？所以本来是 dy over dx， 我讲的是正原来的函数，现在反函数要去看导数的时候，就会变成什么 dy 一点点 y 的改变，去看看会引发多少的 s 方向的改变。所以这两个不是刚好正好相反吗？上下颠倒。所以这个公式说起来看起来很神奇，那说出来事实上就是这个道理。你会发现它刚好是正函数导数的导数，因为两个观点，一个是从 s 看 y， 另外是从 y 看成 x。当然我们把它改成反函数的时候，我们一律都是用 s 当作自变数。所以我等一下举一个例子给大家看。Okay, so I just want to give you an example. That, for example, if f of x is equal to s squared and s is positive or is equal to 0, what's f inverse derivative s is? Okay, so there are two solutions. Solution 1 is, since f of x is s squared, s is positive or equal to 0. So, and y is s squared. And then we can just change the row, become this one, right? We just take the square root at both sides, then we can have this one. Then you can see original by following this for the original function, x will determine y, right? After we change this one, this is the another way to see this curve that we can have y then determine x. But normally when we just express a function, normally we will use x as its independent variable. So we just change y as x and here become y, so that we can get y is equal to square root of x is the inverse of y is equal to s squared. S is positive or equal to 0. So that we can continue, because I want to get its derivative, so that we can just continue to get the derivative for the inverse function. Here we already know its inverse, right? Then we continue to differentiate it, then we can get this one. Then we can get finally it will be this one. So actually so far we didn't apply the theorem, the previous theorem. We just follow that we have the original function, we can get its inverse first, then differentiate the inverse. Okay? And the solution to is because we want to get f inverse prime of x by the theorem 1, that we can get it as 1 over f prime of f inverse x. So that, how can we get that? So f prime, so original f of x is s squared. Therefore, f prime x should be 2x, right? And we already know f inverse of x is equal to square root of x here. We already know its inverse. So that with this, we can have 1 over 2x let me just show you. F prime of something, right? So please just hide this one first. F is the original function. We just try to get its derivative first. So f of x is defined as x squared. So please just hide this one first. Then we can get f prime x is 2x by following the original function definition. Then we already know f inverse x is this one. So we just use this as square root of x as the input here, so that we can get this one. So finally, you can see both of them are the same. One is here, one is here. One is here. The only difference is for the solution 1, we just get its derivative, its inverse first, then differentiate it. The solution 2, we just follow the theorem 1 to get its inverse. So finally, you can see both of them have the same result. Both of them have the same result here. Okay. Then I will give you another example. Is that okay? So sometimes when you just, if it's your first time to understand what the inverse is, normally it will confuse you. Because when you just get its original function, then try to get the inverse function, you should follow this way. You should follow this way. Original, it should be y is equal to blah, 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 x. So you need to find some way to convert it into s is equal to blah, 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 y. Let me just repeat the idea again for you. If I give you the original function is y is equal to blah, 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 s, you must find some way to convert by following this equation. To convert it, become s is equal to blah, 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 y. Then change the variable. S will become y, y will become s. Then you can get this inverse. So I also did some questions in this section that you can have more practice. Of course, this one is very, very simple. But before you conduct to get the inverse, you need to make sure it should be one-to-one function first. And then if it is a one-to-one function, then you can make sure it can have a inverse function. Then we can continue to get its derivative. And the derivative, you can follow this theorem. Okay? So let me give you an example that f of x is equal to s cubed minus 3 minus 2. Find the value, this one, at s is equal to 6 without finding a formula for f inverse of x. So the question has some comments that you cannot just find the formula for f inverse, then get the result for this question. Can you just directly get this one? This is our target, right? So if the question just requires you to calculate the inverse at s is equal to 6. So if s is equal to 6 for inverse, that is from f inverse viewpoint. This is for f inverse viewpoint. But if we want to convert it from f viewpoint, here will be y. So that means when f of x can be 6, what this x is. So you can see, let me just repeat the question again for you. If I ask you to calculate the derivative for f inverse when s is equal to 6, even though here is x, but for f inverse, if this is x, for f of x, it should be from y. So that means when f of x is equal to 6, that means what is this x is? We can get y is equal to 6. Okay, so based on this idea, so we can see 6 when we can get this one for 6, that means a is equal to x cubed, so that s should be 2. So this is for the original function's viewpoint. So that means here, that means for f of x viewpoint, when s is equal to 2, we can get f of x is equal to 6. But for inverse, this should be x. For the original function, this should be x. Okay, so this is x. This is f of x. This is x for different angles. So after this, then we can note by theorem 1. If you want to calculate the inverse when s is equal to 6, that means it should be f of 2. Because when x is 2 for the original function, we can have its function value as 6. Okay? So this is f of 2. Then when you want to calculate its inverse, you can get the inverse of the original function. That means this one. Then when s is equal to 2 here, not 6, here should be 2, because when s is equal to 2 for the original function, we can have a return value as 6, even though here is x, but s is for inverse function, not for the original function. Okay, so that we can continue to get the result as since the original function is s cubed minus 2. This is the original function, right? This is the original function. Then we can get f is equal to 3x squared, so that we can have df dx when s is equal to 2 as 3 times 2 squared. So that will be 12. So finally, the answer will be 1 over 12. This is the answer. I just make it smaller so you can have a whole picture of this. Okay, this question just asks us to find the derivative for f inverse when x is equal to 6. If I give you the original function, it's f of x. But you cannot find the formula for the f inverse. Can you just directly apply the theorem 1 to get the answer? So you can just think about that okay, you just asked me to get the derivative of f inverse at s is equal to 6. So remember, x here is for f inverse, but for f or original function, it should be y. So that means we need to get when what s can cause a return 6 for the original function, right? So after this calculation, we can note for the for x is equal to 2 and the original function is this one, we can get the return value is 6. So this is exactly what we want to get. Because we get this one, we can just follow the theorem one, that when you want to calculate the derivative of f inverse at s is equal to 6, that means f of 2 we will have 6 here, so here should be 2, right? So we already have the original function f, so when we differentiate it, it will be 3x squared. So with 3x squared, when we put 2 as the input for this part, and then we can get 12. So finally, the result will be 1 over 12. Okay, so this is for the section 1. One to 6. Okay, so for the serial 1 in chapter 7 is very important, because later on we also apply the theorem to get the inverse of some specific function. So you need to get familiar with the theorem 1, because we will frequently use this theorem to get the derivative of some inverse function. Okay, this is section 1. Then we will move to section 2. We will talk about the natural logarithm. I believe maybe you didn't learn this before, and I'm not sure if you know this number, e, constant e. The function value is 2.7828459045233536. It's just like pi. It's a irrational number. So endless. You just know it's just around between 2.7 to 2.8. But you cannot exactly pinpoint this position for this point. Just like pi, right? We know pi is a 3.14 blah blah blah, right? And for the constant e, it should be 2.718 blah 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 blah. So before we want to know this number, we need to give a formal definition for the natural logarithm function. It will define like this way. The natural logarithm function will be ln x as its input. Ln is a function. It will be defined as integrate from 1 to x 1 over t dt. Then s should be positive. So that means it's almost like this one, that if this is t, then this is 1 over t. So there is a start point 1, right? 1 almost here. This is a start point, but the x is a variable. It's variable. It's a value. So, for example, if S is here, it's just like you are trying to get, if you want to get ln x, it's almost like you try to get the area, right? So ln x here, ln x here, ln s here, if s is positive, it's almost the same that you are trying to get the area under this curve, 1 over t, between 1 to x. So x is possible here, s is possible here, right? Of course, s also is possible here. But for x is larger than 1, it is almost equal to the area under 1 over t from 1 to x. So if x is larger than 1, so that means the x at the right is on the right hand side of 1, then when you calculate ln x, it will be 1 to x 1 over t dt. It should be positive, right? Because we are talking about this part, so this part should be positive. ln x should be positive. If s is equal to 1, then we can get ln x is equal to 1 to 1 over t dt. So it will be 0. And if s is less than 1, ln x is also 1 to x 1 over t dt. So we can change the direction to negative x to 1 over t dt. If x is less than 1, so that means x should be here. X should be here, right? So we can change the direction from originally is 1 to x. I change the direction. By putting negative sign here, we can get from x to 1, right? X to 1. So negative times positive. So this part will be negative. So with this, we can get, if x is larger than 1, the function value will be positive. If s is equal to 1, the function value will be 0. If s is less than 1, the function will be negative. Actually, I can show you first, but later on I will also prove this part. Actually, the function will look like this one. If y is equal to ln x, it will be an increased function. It will be increased function. Later I will show what is the increased function, but the function is just the function value is like this one. When s is larger than 1, it will be positive. When s is equal to 1, it will be 0. When s is less than 1, the value will be negative. Later on, I will show you the result. This is the first definition. The second definition is the number e. I just show you here, right? The number e is here, right? The number e is defined as the number satisfying ln e should be 1. ln e should be 1. So you just think about that. E is some number here, but it needs to satisfy that ln e is 1. What does it mean? What does it mean? That means the area should be equal to 1. For example, in the beginning, if 1 is equal to, for example, if x is equal to 1.2 around here, so you can carry the size, the area, right? Move to 1.5, you can get the area. Only the size of the area reach 1, then you will stop. You will stop. Then when the x can cause the area size is equal to 1, then you stop there, then the number will be that number E. Here. 2.71828818 blah 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 blah. This number will cause the area size become 1。我很快定一下这个1这个数字也许你们过去有学过老师可能有讲过呢，但是不确定了不确定，因为每个人的这个高中高职学的东西不一定一样，没关系。这里呢，我希望大家就 reset。就把过去的先忘掉。我们先从哪里定义起呢？从这个自然对数函数定义起。什么叫自然对数函数？就是 ln x。x 是我们变数，对不对？那它把它定义成什么？积分从1开始到 x 对1 t 分之一做积分。但是大家可以想象，从图的角度来想 ，t 分之一长相就是一个递减函数，对不对？就是一个递减函数。那从1到 x 的角度来看呢 ，x 假如 x 是大于1了如果我们在算 ln x 是不是等同于在算什么？我们之前有讲过，如果你是个正的函数，其实你积分那曲线的面积大小呢，事实上跟你的积分的结果是一模一样的，对不对？所以我们来看看1到 x 这边都是正的，所以积分从1到 x 的 t 分之一是不是等同于这里的积分面积大小，这块的面积大小。所以呢，如果定义成这样子后，我们分成3个层面去分析它的时候，它会有这3个结果。这个也不赘述那很特别的地方是，它有一个叫 number 1，这个 number 就是常数1，跟派一样。它被定义成什么？它满足 ln 1等于1。这1是谁呢？其实我不晓得，但是它告诉你一个什么条件呢？ln 1要等于1，这个发音刚好都是1了ln 1呢，这个常数1呢，它的面积，大家想一想，如果在这边离开1点点的时候 1.2， 它就有个正数，这就是定义。ln 的 1.5 又得到一个正数 ，ln 的2又得到一个正数。什么时候会让这个面积大小到等于1的时候会停了？停住的那个点就叫1，常数1。这是它的原生的定义。我们等一下来看看这个1跟 ln 函数呢这些相互的一些关系那我们就先休息一下好了等一下，我先把它关一下。这没带滑鼠，很难用。ln x. So if so, can we just try to differentiate ln x. If we try to differentiate ln x, we can see that will become differentiating 1 integral from 1 to x 1 over t dt. So what is the result? 1 over x, not t, okay? So you can see we just apply the fundamental theory of calculus again, right? We just differentiate 1 over t, integrate 1 over t, but differentiate immediately. So the result is 1 over x. So please just keep this in your mind. And we can just extend the idea to if y is equal to ln u, where u is a differentiable function of x. So when we differentiate ln u, so you can see the difference here. Here is x, right? But here is u. So the result will be 1 over u, remember adding du over dx. Right? Do you remember we also can apply the chain rule that you can see when we differentiate ln x, u will be 1 over x. Right? But here is u. U means blah 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 x here. So the result is 1 over u. Don't forget at this part. So let us just give you a try that if we want to differentiate ln of s squared plus 3. So what's the result? That will be 1 s squared plus 3 times this one. Then that will be 2x over s squared plus 3. Okay, so please also keep this in your mind. Then I will show you some property about the ln function. So here is some properties of logarithms. The so-called theorem 2, that for any number a positive a and s is also positive. So remember, a should be positive, s is also positive. The first thing is ln a x will be ln a plus ln x. The second one is ln a over x, it will be ln a minus ln x. The third one is ln 1 over x, it will be negative ln x. The next one is ln x to the power of r, it will be r times ln x. I believe if you just learn the function about logarithm before, log, right? You can also see we can have a similar property about logarithm. So actually, in the later section, we will talk about the general logarithm. So you can see ln is a very special logarithm function when the base is e. 你可以看这 ln 函数有没有似曾相识，很像你们在中学的时候有学过对数函数，有没有？有吗 ？log 函数，所以我就说你们这边请大家遗忘掉过去中学以前学的，以前我们都学什么 log 以2为底 ，log 以10为底 ，log 以100为底这种整数的，或者是你们有处理过有理数的吗？可能没有，对不对？可是这个 log 非常特殊，这个 log 竟然是以什么为底？以这个常数1为底，而且常数1是一个无理数，非常非常特殊。但如果你把那 ln 去换成你们log 是以国中有学过吗？还是高职才学 ？log 的函数以后，你把那 ln 把它改成 log， 你会发现一模一样。我们后面也会证明 log 其实放进来也是一模一样。但是我们先从 lnx 定义学起，所以你看我们是从哪里学的？我们是先从 lnx 等于积分从1到 x 1 over t 去学起来的。我们其实都没有讲什么 exponential 这方面的。那后面我们就证明，这两个其实上是一个 exponential 函数跟 log 函数，事实上它们两个是互相反函数的。Okay, so you can see these 4 properties. And I will just prove one for you. Why? Well, we can have this. If you can prove the property 1, I believe you can just apply the same idea to prove the rest properties. So for the first one, we can see that ln ax, when we try to differentiate it, so what is the result? That will become, you can see here is u, right? Here is u. So we will have 1 over u first, then times dx, differentiate a of x, right? Let me just show you again. And u here is ax. So we will 1 over u times differentiating ax, that means u. So the result will be a over ax, so the result is 1 over x. And at the same time, we already know this one, right? We already know this one, right? So did you just notice that here, when we differentiate it, 1 over x. Here, when we differentiate lnx, 1 over x. They are the same. They are the same. So did you remember if we differentiate 2 functions, we just don't know the original function, these 2 functions, what these 2 functions are. But when we just differentiate it, we can have the same result. We can conclude that ln ax and the ln ax, its difference is plus some c. Did you remember? Corollary 1 or 2, I forgot. If 2 functions, I don't know these 2 original functions are, but I know its derivative. And these 2 derivatives are the same. Then these two original functions, the difference is plus c. Okay, so the result will be like this one. Then if s is 1, so we can conclude that ln a is equal to ln1 plus c, right? Because for all x, this equation just holds. So if we just use x is equal to 1 to replace x here, so we can get ln a is equal to ln1 plus c. What is ln1? 0, right? Don't forget, we just learned this. This is 0. So that means C here is ln A. So let's just get back to ln AX is equal to ln S plus ln A. We just use this to replace here, and then we can get this one. Right? So finally, ln AX is equal to ln X plus ln A. So you can just follow the same idea to prove this one. You can just follow the same idea for prove this one. And if you have this one, you can get this one very easy, because we just simply let A is equal to 1, right? If A is equal to 1, then we can get ln 1 over x immediately. Then how can we just get ln x to the power of r? Because if we just try to deal with ln to the power of r, x to the power of r, that is equivalent to ln x times x times x, blah blah blah. Totally, we have rx here. So we can just apply the rule 1, RT1, to decompose it, and finally we can see the result. So that's why I do not just prove the rest 3 ones, because you can do it by yourself very easily. Okay. So that right now we already know some property about nx. Then we are trying to get its graph. So the following, we are trying to get the graph and its range of ln x when s is positive. So did you remember when I told you? Actually, I just give you the answer ahead of the time, because actually I didn't prove ln x is just this one. I just let you know first. But here I will prove the property for you that the ln x will follow this. Okay, so through this I will do that. The first property is when we differentiate ln x, then we already know it will be 1 over x positive for x is positive. So based on this, we can know ln x is an increasing function. Did you still remember? We can use the first derivative to understand the function is going down or going up, right? Going up or going down, right? If the first derivative is positive for some certain interval, we will say the function in that certain interval can behave in an increasing way. If the derivative is negative for some certain interval, then the function will just behave in a decreasing way for that certain interval. So with this, because it's positive, so it is an increasing function. I think that shouldn't be a problem for you, right? And we just continue to differentiate this function. That means we just differentiate this, then it will be 1 over negative 1 over x squared. That will always negative. So based on this, we will say lnx is concave up or down. Concave up or down. Here we try to use a second derivative, second order derivative to check its concavity. So it is concave down, right? Concave down。不要忘了呢，这还在我们考试范围哦。一阶导数是来判断它的递增递减性，二阶导数是来判断它曲线在某个特定区间的凹口朝上或朝下 concavity。不要忘了呢。Okay, so with this, we can just try to get the function like, because we know that we are trying to, this is y is equal to 1 over t, right? Then for the function itself, it will be increased, not just passing 1. Here is 0. Then the function will be increasing, but concave down. Okay, so, and then we try to get its range. And its range is, we can just check it that since ln 2 to the power of n will be n times ln 2. What's ln 2? ln 2 is, here is 2. So ln 2 means we are trying to calculate this one. This is ln 2, right? Because ln 2 is equal to integral from 1 to 2, 1 over t dt, right? So suppose this is ln 2. So when we just think about ln 2 to the power of n, we can just simply move the n to the coefficient times ln2. So ln2 should be this area. This area in yellow. But we also notice that this part will larger than this 2 here should be, this point should be 1/2, right? And this is 1. So suppose n times ln2 must larger than n times 1 times 1/2. Because you can see yellow portion is larger than the blue one. Right? So with this, here should be n over 2. Hence, when n is approaching positive infinity, that implies that s is approaching positive infinity. Then we can see ln 2 to the power of n is also going to positive infinity. You can see if n is going to positive infinity, that means s is also, actually, it is not a serious proof, but you can see 2 to the power of n can represent many points, especially when n is approaching positive infinity, as the corresponding x value should be also is approaching positive infinity. So finally, here is positive infinity. So this number will also is approaching positive infinity. So similarly, for second part B, when we think about ln 2 to the power of negative n, that will be negative n times ln 2. That will be less than negative n over 2. Follow the same similar way. So when n is approaching positive infinity, that means s is approaching 0. Why when n is approaching positive infinity, n is approaching 0? Because here is 2 to the power of negative n. So as n is increasing, then the value will be, the x value here will be decreasing and approaching 0. So based on this, you can see the function value here, ln 2 to the power of negative n will approaching negative infinity. So with this, you can see as x is become very large, then the function value will be positive infinity. As x is approaching, decreasing and approaching 0, then its function value will become negative infinity. So you can see the domain So by these two facts, by A and B, we can conclude that limit s is approaching positive infinity, ln x will be positive infinity. And when limit s is approaching 0, that will become negative infinity. So we can get the result. And we can also conclude that the domain for the ln x will be from 0, not including 0, to positive infinity. But the range of ln x will be negative infinity to positive infinity. That's very important. So we can roughly conclude that when s is approaching positive infinity, the function value will go to positive infinity. When s is approaching 0, the function value will go to negative infinity. So if we can get the inverse function for ln x, you can just guess that the inverse function for ln x, the domain will be negative infinity to positive infinity. But the range for the inverse of ln x, that will be 0 to positive infinity. 所以这边做一个小小的总结哈，这边是不是很严谨的证明了什么？就是没有很严谨的证明出 ln(x) 它是个函数，我们就要探讨它的domain跟它的定律跟值域嘛。那我们去尝试取出它的定律跟它的值域是怎么做呢？一个我们去考虑2的 n 次方，一个是考虑2的负 n 次方。那你会说2的 n 次方其实不能涵盖所有的 x，
但是它约略可以看出 x 很大的时候的一个情境啊。其实在下学期我们学到数列级数的时候，事实上连续函数跟离散的点，有时候它们有些时候事实上是命运共同体。离散的点它怎么样的一个走势呢？有时候跟它所附着的函数是有相关的。所以你不妨这样想，我其实要探讨所有的 x， 虽然我没办法一列举出来，可是2的 n 次方某种程度带出很多属于这方面的点，包含比方说 n 等于1的时候是2、4、8、16、64，对不对？当然它不是代表所有的 x， 可是呢，某种程度我们看出它的趋势，就是整个值会朝向正负大号，所以我说这不是很严谨说明这个domain。相反的，如果是 Ln 的负 n 次方的这个形态的话，你会发现它的值随着 n 一样很大，代表什么？一开始是0， 1的时候会是什么？负1/2，再负4/1，负8/1，负60/1，负一个很大的2的 n 次方分之一，最后没有碰到0哦，很接近0，可是它呈现出来的值会往负成大。所以一样的，你这边也只有离散的点，可是它事实上它离散的点怎么好，事实上跟它某种程度反映出它的连续函数。所以我们就透过这两个性质呢，得到它 Ln(x) 函数的domain跟它的 range。那同时伴随刚刚有什么？
它的一阶导数是大于0，所以是递增函数。它的二阶导数是小于0，所以它是开口朝下的。所以最后呢，瞎子摸象，我们收集了几个资讯之后，它的图形就会长像这橘色这条曲线的长相。
从比0多一点点开始起跑，这个值会非常的小，负的非常大，一直到经过0，一直到0的时候，一路都递增，而且这递增的过程当中，它是开口朝下，然后呢，在往上跑的时候呢，它又会递增，开口继续朝下。那后面我们会讨论到，我们先跟大家讲 ，Ln(x) 函数它是一个递增函数，它是就像我们说什么 y 等于 x 平方，它也是递增函数，对不对？y 等于 x 的5次方也是递增函数 ，y 等于100次 x 的100次方也是递增函数 ，y 等于2的x 次方也是一个递增函数。那 y 等于 Ln(x) 它也是个递增函数，可是这几个递增函数里面虽然大家都往无穷大跑，可是 y 等于 Ln(x) 函数在走的时候是相对于其他函数来讲比较慢的。龟兔赛跑那个听过对不对？乌龟走得很慢，它也是往目标在走。那个兔子跑得很快，也是往目标在走。那目标是什么？都是无穷大。可是 Ln(x) 虽然走得慢，可是它最终的目标还是无穷大。走得再慢还是无穷大，相较于这个虽然 exponential 很快，所以后面我们在讨论这函数为什么，如果你后面是选择计算机科学或者不一定念计算机组，我们常常去讨论这些复杂度的时候，我们常常就会拿这个来譬喻，就是说大家都是这 n 带进去的时候呢，就函数的 loop， 就像你们在写程式有那个 loop， 对不对 ？loop n 次。它如果你走一个演算法 ，loop n 次，它走出来的效果是指数型的，或者是线性的，或者是抛物线的，这些都很快。Ln(x) 算是最慢的，但是它其实是随着 n 越来越大，它所使用的计算资源也是越来越大，只是每个大的程度又有特大、次大、小大跟很缓慢的大。所以这个让大家稍微知道一下这个性质哈。OK， so I will continue to introduce some properties about Ln(x).
So this one will be, we already know this, right? We already learned this. We already learned this, right? When we just differentiate ln u, the result will be 1 over u times du over dx. So if I try to integrate both sides, so we still can keep the equality. So this will be d ln u 1 over u du dx. So what will happen? What will happen? For this part, for left hand side, you can see we try to differentiate ln u, then integrate. So that will come out ln u. For the right hand side, you can regard this as differential. So we can just cancel that. So finally we can have 1 over u du from the right hand side.
But since this is a indefinite integral, so here
For the right hand side, we need to have plus c. So finally we can conclude that. Integral 1 over u du is equal to ln u plus c. So this is also very important. So if u is positive, so we just simply get integral 1 over u du is equal to ln u plus c. But if u is negative, so when we just calculate this one, since u is negative, we can just add in negative here, but also d negative u here. Actually, they are the same, right? But the result will be, after we just change it, then we can get, it will be ln negative u plus c. Because here, right? So finally, based on these two facts, we can get integral 1 over u du is equal to ln, taking the absolute value of u plus c. So
for these two ones, we need to analyze if c is positive or negative, whether c is positive or negative. But with this, we don't need to care about it is positive or negative. Just simply put the absolute value for
here. So now, this is the first important result. And also we can conclude another result, that integral u to the power of n du. So in the past, did you still remember when n is not equal to negative 1? At that time, we already know the result. It will be 1 plus over n plus 1 u to the power n plus 1 plus c. Did you remember? For n is
not equal to negative 1. Because in the past, when we talk about, when we want to take u to the power of n, we want to integrate u to the power of n, we just ignore n is equal to negative 1.
n is equal to negative 5. So that means if n is not equal to negative 1, we can have this result, right? Just simply increase the power n to n plus 1, and adding the coefficient 1 over n plus 1 here. But right now, since we just introduced the Ln function to you, that we can just add this part for n is equal to -1 here. So the answer here is Ln after the value u plus c。好，过去的时候，我不晓得大家有没有注意到啊？以前我们在讲u 的5次方的积分 ，u 的负2次方积分，我们怎么做？我们是把那个幂次加1，这个幂次加1，它是绝对补一个1加上幂次加1的起数。其实你们那时候不知道有没有注意到，我们都没有去碰触一个，如果 n 等于负1怎么办？所以过去其实我们出的这个题目的时候，这个都没有 n 等于负1的状况。在这里我们把它补足了。n 等于负1的时候，它会变成另外一个 n 的形态，不是这个。所以要注意 ，n 不等于负1的时候是这一个，但 n 等于这是一般我们过去所学的，但是如果 n 等于负1的时候是这一个。So on the other hand, we just let u is equal to f of x, then du over dx is f prime x. So we can have du is equal to f prime x times dx. So if we just encounter 1 over du, 1 over u, du. If you just face this one, we can just replace it as we just let 1 over f of x, right, times du is f prime x dx. So finally you can see integral f prime x over x dx, then the result will be ln taking the actual value of x, f of x plus c. So finally, this part is very important, but I will show you some example for this case. So when you just encounter the integrand with f prime x over f of x form, the result will be this one. So on Wednesday, I will show you. In this case, no matter you need to choose a suitable substitution for this form. Okay. So maybe on Wednesday, I will give you some example to introduce this part to you. 好，那我们就先上这里哈。礼拜三我们再举个例子给大家看。